we are going to talk about how to select your own workload for your system. And obviously the key is services that you are going to use from that system. So we will take some examples and then we will go through some issues about levels of details, representativeness, timeliness, and other considerations. So there are 5 total considerations: services, level of detail, loading level, impact of other components, and timeliness, and we are going to discuss them one by one. So let's see. First of all, you have to identify 2 items. One is the system under test, and second is the component under study. And generally in the benchmarking world, we use the word SUT very often. SUT is S-U-T, system under test. All right. So component under study might be a piece inside the system under test. For example, you are buying a disk for a system, so the system under test is bigger, but the disk is your component under study. Right? Then you have services. At this level, you want to see whether this disk is better or some other disk is better. Whether it should, if you, for example, you might want to find out how much a SSD will improve the performance compared to a hard disk. SSD is the semiconductor disk, right? So that would be your component under study, and the disk, and then here system. And there might be some other thing outside that may also affect the performance, by the way. So the network and other things. So first of all, that now we have to worry about the services exercised, and the services determine the workload and the matrix. So we already talked about the matrix. To find the right metric, what you have to do is you have to make a list of all the services. For each services, you have to make a list of all the outcomes, and then you have to write down the probability, rate, resource, time, etc., etc. So now what do we do for the workload? Okay, first of all, do not confuse SUT with CUS. Okay, so here are 2 different problems. Suppose so you are looking for a disk. You are comparing. You work for a disk manufacturer. You work for a disk manufacturer, and you are comparing 2 different disks from the same manufacturer or with the competition. Then what is your system under test? Disk. On the other hand, you work for Dell, and Dell doesn't make disk. Let's just assume for the time being, and they are making a PC, and they are comparing 2 disks for the PC. Right? Their case, the problem is different. In their case, the system under test is the PC, and this is little component under inside. While in the previous problem, one disk may be twice as fast as the other. In this case, it may be just 10% difference, because the workload does not need the disk. You see? And so do not confuse SUT with CUS. Make sure that you understand who you are working for and what you are comparing. Right? You are not comparing the disk as they are. You are comparing PCs with different disks in it. Clear? Yeah.
The first example, are they equal?
Oh, in the first example, are they equal means?
Yeah, if I'm just comparing the disk.
Yeah. Then the performance would be basically, you will have your services would be very different. So what is the services for a disk? What services does disk offer? Anybody?
Sorry.
Eh?
But the system under test and the component will be the same.
Will be different. Let me just say one more. First of all, yeah. So what you are saying is, when you are doing the disk, then and you are comparing 2 disks, then the system under test is the disk and the component under study is the disk. Quite possible. But if you are working for a disk manufacturer, it is also another problem could be that you are comparing the disk, but you are comparing the 2 different mechanisms inside, the head mechanisms inside. Who knows? So it could be possible for that problem, component is different. So the component could be equal to the system, yes, in any case. I mean, now you don't work for Dell, you are working for Vashu and you're looking for the PCs. Now you're not going to look inside the disk, you are just going to look at two PCs from the outside. Right? So the component under study is same as the system under test. Right? But, so remember this, that you really care for the services offered by the system and not for the component. The component makes a difference, but if we don't exercise the component, then the system will not have to see any difference. If you have a very heavy I/O workload, then disk matters. If you have very communication-oriented, network-oriented workload, then this network speed matters. On the other hand, if you are not going to use any of that, then it doesn't matter. Your services will have the same performance, right? And so both ways it works. Oftentimes I read papers where people say, well, we compared these two things and the network makes no difference. All right? So what they are concluding is that they didn't really use the network. Not that the network makes no difference. Their workload was such that it didn't use the network. Right? So when two things look equal, they may not really be equal. They are equal under that workload. The moment you change the workload, the things will show up. So here's the thing: if you do have a component under study, then make sure, if you really want to study the effect of that component, make sure that that component is exercised. Right? Otherwise, your problem might be simply to figure out whether the system will have any performance, and you are given the system service and you know what you are going to use the system for, then you use it for that workload, and your conclusion may be different. We'll say that, well, really the disk speed is not the problem, because disk is not the bottleneck, it's the network which is the bottleneck, and therefore we can just go with the hard disk and not worry about SSDs. Right? So it depends upon what level you are looking at. So first thing here, do not confuse SERT with CUS. Matrix depends upon the SERT. MIPS is okay for 2 CPU but not okay for 2 time sharing systems, because in the time sharing systems you have CPU plus a lot of other things like network. Workload depends upon the system. So if your system is CPU, then you can use instructions as a workload. If it is a system, then you probably will use transactions, and transactions are not good for CPU because performance of the transaction depends upon the CPU, disk and many other things, and vice versa. 2 systems identical except for the CPU. If you want to compare 2 systems which are identical except for the CPU, so your component under study is CPU, you have 2 different CPUs and you want to compare, then yes, then you will use transactions to compare the systems and see whether the CPU makes a difference for your transactions. Or if you want to compare CPUs, then you will use instructions. Now multiple services, exercise complete set of services as possible. So that's the thing, is that your system, you cannot just compare on one service. You will have to, whatever it does, say for example we talked about read and write. If you are just simple disk, you need to know both the read speed and the write speed at a minimum, right? Then you might go for reliability, energy consumption and other things. So you have to put it as complete as possible. All right. So that is one. So, yeah.
Is the effect depends on the system or really on the services? Which depends on the system?
Oh, okay. No. So the thing is, matrix depends upon the services, right? But the services depend upon the system. What is your system? So for example, if your system is a disk, then there are 2 services it offers: write a data block and read a data block. And then if your system is a PC, it offers many different services, including, get to a web page, or edit a file. Those are the services that the system offers, right? And so if you make a list of your services, then you have to write the matrix for those services. You rate time, resource stuff, and the probability, failure, and other things. Now you can extend all this to your own system. If you are doing a PhD and then you have an algorithm where all this PC etc. doesn't matter, really you are comparing two different algorithms, then you have to find out what is it that this offers. I mean, in your case, you have this fall detection, right? So fall detection, you could figure out as to what is it that my system is supposed to do. Very reliably tell that somebody fell down, and then you start from there. Alright, so I will give you some example here. This is an example, not a case study. And the example is basically a time-sharing system. A time-sharing system can be modeled at any level. For example, ALU. Everybody knows what is an ALU? So inside the CPU there is particular thing which does the computation, and so that is ALU, arithmetic logical unit. And then along with ALU you have some more hardware, and that makes a CPU. You put some software on it called operating systems, and then that makes something, and on the top of operating system you can put some applications to run on it. So most of us only see this level. We only get everything ready made for us, and so we are measuring at this time the performance at this level, and therefore our metric would be transaction, our workload would be transactions, and we will use some kind of application level benchmark. On the other hand, if you are trying to compare without the applications, then you will need some benchmarks that will be exercising the operating system, right, like a synthetic benchmark program. Coming down, if you really don't have an operating system, you are comparing CPUs, then you will have some instruction mixes. And again, we didn't talk about instruction mixes in the class, but please read it in the book. It's so straightforward that I thought it is important to do it, important to do this other stuff. And coming down further, if you go to ALU, then you start using the addition instruction. So that was one of the first benchmarks, was the add instruction. And you may still use it if you are comparing ALUs, which people inside Intel probably are doing, but most of us don't care, to that level. Okay. All right. Another example: networks. Some of you have taken networking course. So if you know, then the networks have 7 layers: physical layer, data link layer, network layer, transport layer, session layer, presentation layer, application layer. The applications are like mail system or file transfer or something, and so on and so forth. You come down. So if you are measuring the performance at the physical layer, you will measure it in measure basically the bits. At the data link layer, you measure the frames. At the network layer, you measure the packets, and so on. I mean, if you don't know networking, then I don't want you to get into this. It doesn't really matter. If you know networking, then you will know that at every layer there is a different set of services that is offered. Right? The network layer handles the packets, transport layer handles the messages, and so on and so forth. And therefore the services are different, and therefore the metrics are different, and the workloads are different. Okay, so much about the services. The next issue that decides the workload is the level of detail. How detailed the workload should be. And so if you don't want to go too much detail, then you take the most frequent stuff, things that are most common, one thing that is most common. So for example, in the case of CPUs, add instruction was selected. Why add? Why not multiply? Right? Because that was the most common instruction. Alright? Our debit credit benchmark, again that was the benchmark that is in the book, not discussed here, is a benchmark which was used because that was the most common application, and so on and so forth. So this is valid only if one service is much more frequent than others. So this would be a good thing. But if you have services which are sort of, not, peaky in the sense that, one thing is more than everything else, then you have to go to the next level. So then what you do is you do the frequency. You say, well, 10% add, 20% subtract, 15% multiply, 20% this, because that is how my real world is. So now you are into histograms kind of thing, as opposed to just one number like that. So you do instruction mixes, and then you have to do whatever set you take, and the main problem is that whenever you have a mix of anything, then you run into this problem where what comes first, what comes in what order. So for example, if you suppose did 10 add instructions and then you did 10 subtract instructions, that is different than add, subtract, because of the caches and other things that can happen. Okay? And in particular, if there is a jump in the middle, that can make even more difference. So if you had add, jump, that would be very different than add, and jump. Right? So the idea is that it's the sequence which is not represented by the frequency. The next level would be sequence. So you take the real sequence, timestamp sequence of request, and that may be too detailed, and this is not convenient for analytical modeling. There is no way you can do analytical modeling if somebody gave you a trace like that. And it may require exact reproduction of component behavior. And also, if you have that detailed model, see, that was another thing, I think, is that is coming up more, is that if you have that detailed workload, you need to have system also at that level detail. If your system level that you are representing, either simulation or analytical model or whatever you are doing for the system, is not that detailed, then there is no point in having that detailed workload. Average resource demand. So generally for analytical modeling, all you need is one number, average. So you say, well, I need 2 CPU per transaction, 2 second CPU per transaction. And then you group similar services into the classes, and you say for class 1 I need 2 seconds, for class 2 I need 3 seconds, for class 3, and so on and so forth. Distribution of resource demands. Now after one number you are done, then you can say distribution. It is exponentially distributed. It is normally distributed with mean and this and variance of that, or it is binomially distributed, whatever. Then you go into the more detail, particularly if the variance is large. And if the distribution impacts the performance, which it almost always does. Workload used in simulation and analytical modeling. So when you do simulation or analytical modeling, the workload that we require is non-executable, as opposed to executable workload that is required when you are doing a measurement. When you are doing a measurement, you really need the transactions detail, that I am going to deposit a check, withdraw money, this and that, right? When you are doing analytical modeling, all you need to know is that depositing a check takes so much CPU time, so much disk time. And so really it's not executable, it's just the specification kind of thing. So that is non-executable workload. So you have both kinds of workload, executable, which basically are something that you can run, and non-executable is just a specification which is, you just know. Okay? Alright. Now, level of detail, I need to tell you a story about this. I think I probably told you in the previous class also, maybe in the very first class I told you. So there was this guy in our group who was modeling a system, writing a simulation for 2-3 years, and after several years I got tired and I said, what are you doing? He said, I'm still simulating. And why? He said, well, because I'm going through this level of, did I tell you about this disk thing? Okay, so I don't want to tell you again, but that is the level of detail that we don't need. Is that he was going to simulate the system at a level at which he did not have the workload. The opposite problem is also possible, that you might have a level of detail of the workload that you do not need because your system cannot accept that. So if you are going to do, let's say, analytical modeling in which all you can do is probably use the mean, at most a variance, and then somebody tells you whole trace, it doesn't matter, because all you need out of that trace is 2 numbers. right? So the level of detail has to be matched with the level of the system. All right. So next thing is representativeness. The test workload and real workload should have the same elapsed time, resource demands, resource usage profile. So basically that is what representativeness means, is that if you run the workload or you run the real thing, you should get the same kind of behavior. And these are actually more and more detailed level of representativeness. Just one number is matching resource demands on every resource is same, like you say, well, CPU time, disk time, so on and so forth. A resource usage profile. This is even more detailed than that. It's not that we just want 1 second of CPU and 2 seconds of disk. We want 50 milliseconds of disk, then go to the 50 milliseconds of the CPU, then we go to the disk. Then we come back and use another 75 milliseconds of the CPU, then go to the disk and do this. So when you need the whole profile, that is the last one. There, it is just not the total or anything. It's how you go from one to the other. All right. So that could be, and if you change any of those, that transition probabilities, for example, in queuing theory, we'll talk about what is your probability of going to the disk 1 or going to the disk 2 or going out. You know, those things, if they change, the performance will change. Timeliness. So what is timeliness? Timeliness means it has to represent today's usage. And the benchmarks get old very fast because the usage changes very fast. So a benchmark which was used 10 years ago may no longer be good today because people don't use the computers the same way they used to use 10 years ago. Right? 10 years ago there was not that much graphics, not that much of internet, and so on, right? Now the workloads are very different. And so whenever so same thing applies to algorithms or whatever you are doing, you have to find the current usage. And that is one of the problems is that anything that you have done, it always takes 1 or 2 or 3 years to gather it, summarize it, analyze it, and by the time you are ready to use it, somebody says, no, that's no longer valid. Right? So new systems means new workloads. Users tend to optimize the demand. And so the thing is, as soon as you change the system, the workload changes. Right? If my computer was slow, I would do very different things. I would try to avoid network as much as possible or disk as much as possible because I know that is kind of a slow thing. On the other hand, if I get a fast disk or fast network, then I'm downloading 50 megabyte files. Or, even nowadays we don't even think about 5 gigabyte files. Right? Previously we couldn't do that. So the workload that was measured 5 or 10 years ago is no longer good because that was designed for the old days. Right? So user tends to optimize the demand. That's what it means, is that the user's behavior changes with this system. So this is the kind of thing, you optimize for one workload and you give them another system, now they are totally different workload. Fast multiplication, if the multiplication is fast, then higher frequency of multiplication. That's the same thing like, we talked about the file transfer. Important to monitor user behavior on an ongoing basis. So the companies for whom it makes a difference, such as Microsoft and Intel designs the hardware, Microsoft designs the software. They monitor user behavior on an ongoing basis. There is a whole set of people who are working on monitoring what people are doing and then setting up the workload so that the new designs can be tested on those. All right, other considerations. Loading level. A workload may exercise the system to its full capacity, beyond its capacity, at the load level observed in the real workload, or may be typical, and so on and so forth. So there are 3 levels at least. You could run it at the full capacity and or beyond the full capacity. Beyond the full capacity, remember that fall off the cliff behavior. So you want to find that out. Worst case, best case, and typical case. When you want to buy something, you generally go for typical. When you want to design something, you generally go for the worst. I mean, not always, because if the worst is going to increase the price by 10 times, obviously nobody will want to design it, but you want to make sure that it is, your system is not really just doesn't fall off when the load is at some point, right? So that's why you want to make sure that the worst case is non-zero. All right. Impact of external components. So there are certain things that are not in your system and they can affect your performance, right? And so you do not use a workload that really depends upon that other thing, because either you will be penalized or you will benefit from that other thing which is not really your business. So all alternatives in a system give equally good performance, and that's what happens, generally when anytime you see a study which says that, well, we are as good as them, or which is very common, is that or it doesn't really make a difference. So for example, very recently somebody was making a presentation, one of the students in something, and then he says, well, this parameter X, we tried 5 different values and it makes no difference. So the key question is, you tried 5 different values, but your workload didn't maybe use any of those values. Right? So you have no difference. It doesn't mean. So then we told him that, well, really what you need to do is, this will be required only if you have a file, say the files which are bigger than your disk or something like that, and therefore you will have to do this and that. If you use that workload, then maybe this parameter will make a difference. Right? So that's the kind of thing you have to go into the system, is when you get a result, you have to explain why it is and what could have made a difference. Again, this is all very art part of it. I mean, there is no science part of it. I mean, in the sense that there is no one rule I can give you, except lots of examples. All right, repeatability. So that's another thing, is that really anything that we do, we need repeatability, because we have to tell it to our bosses, and they have to tell to their bosses, and they have to tell to the customers. And if you found something that is just not repeatable, then it doesn't really help. That's why we don't use the real workload. Real workload means we don't put real people, because then we cannot repeat it. Okay? All right, that's the end of this chapter. It's a very short chapter. And now you have some hints about how to select a workload for your own problem. The key is the services. Remember, this key, services was the key for the matrix. Now services is the key for the workload. And then the second thing is the level of detail. So the level of detail should match the system level on knowledge or model that you are doing. If you are modeling the system at a very high level, you need a workload at a very high level. If you are modeling the system in very much detail, you need the workload at very much detail. Because if you have the very high level workload and you are modeling the system at very high detail, there's a mismatch, and you will really not get the right answers. Workload should be representative of the real system usage in the recent past. So timeliness is another one. The loading level, impact of external components, and repeatability are the other criteria. So those are the other things. Is how much does it load? So there is another problem sometimes we get into, is that people will have a workload which loads only 10%. At 10% they will show that nothing makes a difference, which is true. Nothing makes a difference, because at 10%, remember, if you take the response time, it is horizontal up to the knee, and then it goes up. So if you are below the knee, nothing makes a difference. Right? So that thing is, loading level has to be representative of the real workload. Impact of the external components and repeatability we talked about. So this is homework number 5. Now you have to, so in your previous homework that I returned to you, you just did whatever way you thought appropriate, and I was very liberal in giving marks because you didn't really know at that time what is the right way to do it. But now you know how to select the right metric, so we'll be kind of strict about how you select the metric at the workload. So now what are the metrics and workload you would choose to compare two systems with similar functionality, IBM PC versus Mac? Our two systems were very different applications, PC versus workstations. Our two systems with identical functionality, IBM PC versus Dell PC, which are similar things. Two versions of the same operating system. Actually, we could have put here HP PC versus Dell PC, something like that, because IBM PC somehow is a class. Sometimes people use it then for Dell PC. Two versions of the same operating system, for example, Windows 98 versus Windows XP. Now I should change this example to Windows XP versus Windows 7 or something. Two hardware components, which means two floppy drives. Two languages, C versus Pascal. One metric and workload is sufficient. So now, the answer to this would be you will put one metric, because otherwise you will write 15 services, for each service is 15 different metrics. That will be a big problem. Here you just write one metric and one workload, but you need justification as to why you selected that.